this lecture, we will be discussing about ultrasound imaging and nuclear medicine. Now, in ultrasound imaging, the image is generated based on the propagation of the high-frequency sound waves through the tissues. So this is fast. That means the response from the source of your high-frequency sound to the detector is actually fast. So you can see in real time the image of the organ or the part of the body you're actually looking into. So the structure and dynamic function can be recorded from rapidly moving tissues, such as a beating heart, and visualized at the same speed in which they happen. So basically, as I said, this is in real time. So it's usually used to view the pumping of the heart, if there's any problem with the heart, with the contractions in the heart. So you can use the ultrasound imaging to view that. So it's also safe. So it can be used on almost any subject, including pregnant women and critically ill persons. So unlike X-rays that are ionizing radiations, so you have your ultrasound imaging, which is safe, very safe. It doesn't cause damage to your tissues. It doesn't cause damage to your DNA. So that's why it's the imaging technique of choice in viewing the babies inside the womb of mothers. So with high-powered focused beams, ultrasound can be used for therapies. Now, since we are using high-frequency sound waves, if we modulate, because these are still sound waves, these are waves, so you have your energy in those waves. But if you can modulate the energy in those waves and focus them, they can be used to shatter kidney stones. Actually, it's part of how you do therapies in breaking up kidney stones, similar to radiotherapies. Now, this is an image of the ultrasound. So the fetal image, the one on the left, is a conventional ultrasound image. Now, we also have 3D ultrasound image, the one on the right. So you can see the difference. So the one on the left is the one usually used, you can usually see in viewing the fetal babies in the womb of mothers. Now, the one thing about ultrasound, unlike CT scan, is that they are quite grainy. So the picture is a bit blurred, and there are a lot of grainy effects in that. And then you have the 3D ultrasound. So again, in a similar way how the CT scan was generated, in having multiple detectors at multiple angles, and then the computer build up the image. So something like that. The 3D ultrasound imaging techniques applies a similar concept to that. And you can see here the actual surface of the face of the fetus inside the womb. So unlike X-ray that you can see through cross-sectionally, this one is a bit different. So this is more, you can view the surface, but not so much as the interior structure. Now, we also have Doppler imaging. This is a technique in ultrasound imaging utilizing Doppler effect. So what is a Doppler effect? So if you noticed, when you hear a horn from an ambulance or a police car. So if the police car or the ambulance is moving towards you, the sound is becoming higher and higher in pitch. So it becomes high pitch when it moves towards you, and then if it moves away from you, it becomes lower pitch. So that is the changes in the pitch or frequency of the sound waves of a moving object. So from that, you can deduce, from judging the frequencies, the changes in the frequencies, you can determine now movements, the velocities of objects. Now, in Doppler imaging, we are using the Doppler effect to determine the velocities of moving tissues, for example, blood flow. So this is especially helpful in studying, for example, stroke. So you do Doppler imaging in order to monitor the blood flow throughout your brain. So which part is the blood constricted? There is difficulty in flowing the blood in that region. So you can easily know through Doppler imaging. So to create Doppler images with ultrasound, the probe produces your ultrasound signal. So this is another parang a branch technique from ultrasound. So you have your ultrasound signal with a fixed wavelength. And then the wavelength of the echo can change depending on the direction and angle of the movement of the objects producing that echo. So for the blood flow, the echo comes from the moving particles, which is your blood cells. So you can see now, so based on the frequency that it receives back from the moving, because it bounced back, so the tissues bounce back the ultrasound wave, the sound waves. The velocity at which it bounces back is basically because of Doppler effect, you can know now the velocity of those objects that cause the bounce. So that's basically Doppler imaging. So here is your Doppler image in a carotid artery. So this is again carotid artery. If you remember, this is the artery in your neck that supplies blood to your brain. So this is a Doppler image. So the red ones, so you can see here the differences in the color. So that gives us an idea on the differences in velocity. For example, the reddish one is slower moving, and the lighter colored yellowish ones are the faster moving. So you can see here from the artery, you have faster moving at the center of the artery, and then going up to the sides, it slows down. There's a bit of a slowdown on the movement. So now for nuclear medicine is based on detecting radioactive molecules. Now this is a bit it's a bit controversial when it started because it uses radioactive molecules, and because we know that radioactivity can be harmful to tissues. However, in this technique, we are using those radioactive molecules in just a small amount, such that they won't pose significant threat. Now, to create nuclear medicine image, a radioactive compound must be ingested, inhaled, or injected. So, again, it's radioactive, so it can cause ionizing radiation. But then again, to minimize the harmful effects of that radiation, we are just using the radioactive materials that are not so strong. So that means you have the radioactivity level is not so high, such that it can cause significant damage to the body, and it's also in minute quantities. So in your nuclear medicine, you ingest, or the radioactive particle, the radioactive molecule is ingested. You take it as a pill, or it can be injected directly to your bloodstream, or you inhale it. Well, if you're looking at, depending on what organ you are actually looking at. So if you're, for example, looking at your for example, brain positron imaging of the brain, so you want to see how you want to image the brain using nuclear medicine. So it's usually injected in the bloodstream, so, and then it will be allowed to circulate for a while. So it's inside now in your bloodstream, and then you will go to your detector. So you are not the source of the or rather, you are the source. If you unlike X-ray, that we have the source of the X-rays and then it passes through your body, this time you are the source of the radioactive signal, and the radioactive signal will be detected. So the organ from your body, since the signal comes from the radioactive particles that was inside your body now, so it will be detected by your detector, and then passes through several, so collimator, detector crystals, and then you have a photomultiplier tube array, and then it will go to the logistic circuits, and then it will be analyzed by the computer. So this is a gamma camera, so it will create you an image of the intensity of the radioactivity from the emitted from your organ. So basically, this is another view of that. So this is an example of nuclear medicine. So there are different techniques in nuclear medicine. One of them is PET scan, or the Positron-Emission Tomography scan. So for the PET scan, the radioactive molecule you are using is oxygen-15. So it has a half-life of 2 minutes. So that means that for a certain concentration, it halves, or it reduces to 1/2 for every 2 minutes. So you have a decay. So the positrons, when they decay, it produces positrons. So if you remember from your radiochemistry, or rather nuclear chemistry, back in your Gen Chem, so positrons are positively charged electron-like particles. So these are these are antimatter particles. So when they encounter your electrons from other cells and tissues, they annihilate each other, and due to that annihilation, your light, so wavelength in the form of light, will be produced. That light is now being detected by your detector, and then of course from the detector you will know now in which part of the body that signal is coming from. So in short, you will produce image like this one. So in here is image slices of your brain in a PET scan. So you are unlike the CT scan where you see the actual lines, the brain is this one, it's well defined in the lines. In PET scan, it's not. You are going to see just the image showing how the dense concentrations of the light sources. So for example, the lighter part, there's a high density of the radioactive material here. So that part is usually very active because the blood supply there is there's a lot of blood supply there, for instance. So these are images that you see. So you cannot really distinguish much of the actual structure, but only where the molecules, the radioactive molecules, can pass through in that tissue. That is why PET scan is usually done in tandem with structural MRI, or even superimposed into a CT scan image, so that you will know in which part exactly the signal comes through. So that's it for nuclear medicine. So in the next lecture video, we will be discussing about optical bioimaging.